Machine learning, ML. Machine learning, ML, is a branch of artificial intelligence, AI, that focuses on the development of algorithms and models that allow computers to learn from and make predictions or decisions based on data, without being explicitly programmed. ML models improve their performance over time by recognizing patterns in the data and adjusting their behavior accordingly. Machine learning can be broadly categorized into three types based on the way the model learns from the data. 1. Supervised learning. 2. Unsupervised learning. 3. Reinforcement learning. Supervised learning. In supervised learning, the model is trained on a labeled dataset, meaning that each input in the dataset is paired with the correct output. The goal is for the model to learn a mapping from inputs to outputs so that it can make accurate predictions on unseen data. Key concepts: training data, a dataset consisting of input-output pairs, for example, images labeled with the correct category. B. Test data, data used to evaluate the model after training. C. Loss function, a function that measures how well the model's predictions match the actual output. The model's parameters are adjusted to minimize this loss. D. Overfitting/underfitting. I. Overfitting, when the model performs well on the training data but poorly on new data, test data, often due to learning noise or irrelevant patterns. 2. Underfitting, when the model is too simplistic to capture the underlying patterns in the data. Algorithms used in supervised learning: linear regression, used for predicting a continuous value, for example, predicting house prices. Logistic regression, used for binary classification problems, for example, email spam detection. Support vector machines, SVM, used for both classification and regression tasks. SVMs try to find a hyperplane that best separates data points into different categories. Decision trees and random forests. A decision tree splits data based on certain criteria. Random forests combine multiple decision trees to improve accuracy and prevent overfitting. K-nearest neighbors, KNN, classifies data points based on the majority class among the K closest data points in the feature space. Neural networks model complex relationships in the data using layers of interconnected nodes, neurons. 2. Unsupervised learning. In unsupervised learning, the model is trained on data that is not labeled, meaning the output is not provided. The goal is to identify hidden patterns or structures within the data. Key concepts: clustering, grouping similar data points together based on their features. Dimensionality reduction, reducing the number of features in the data while retaining as much information as possible. Anomaly detection, identifying unusual or rare data points that do not conform to the general pattern of the data. Algorithms used in unsupervised learning: K-means clustering, partitions data into K clusters by minimizing the variance within each cluster. Hierarchical clustering, builds a tree of clusters, dendrogram, and can be used to group data at different levels of granularity. Principal component analysis, PCA, a dimensionality reduction technique that transforms the data into a new coordinate system, making it easier to visualize or process. Gaussian mixture models, GMM, a probabilistic model that assumes the data is generated from a mixture of several Gaussian distributions. Autoencoders, neural networks used for dimensionality reduction, where the network learns to compress the data and then reconstruct it. Free reinforcement learning. Reinforcement learning, RL, is inspired by behavioral psychology and involves training an agent to make a sequence of decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties based on the actions it takes. Key concepts: agent, the entity that makes decisions. Environment, the system with which the agent interacts. State, the current situation of the agent in the environment. Action, the set of possible moves the agent can make. Reward, a numerical value given to the agent as feedback for its action. Policy, a strategy or function that defines the agent's behavior based on the state. Value function, a function that estimates the long-term reward of being in a given state. Algorithms used in reinforcement learning. Q-learning, a model-free algorithm that learns the value of actions at different states in order to maximize the total reward. Deep Q networks, DQN combines Q-learning with deep learning techniques, using neural networks to approximate the Q values. Policy gradient methods, directly optimizes the policy by adjusting the parameters of the agent's action selection process. Actor-critic methods, combines value-based and policy-based approaches to improve both action selection, actor, and value estimation, critic. Key components of machine learning systems. Data, quality and quantity. The performance of an ML model heavily depends on the quality and quantity of the training data. More and better data typically leads to better model performance. Data preprocessing. This includes data cleaning, handling missing values, normalization, scaling data, feature extraction, and data augmentation. Model selection and evaluation. Choosing the right algorithm is crucial for achieving good performance. Cross-validation, a technique for evaluating models by training and testing them on different subsets of data to avoid overfitting. Performance metrics. Common metrics include accuracy, precision, recall, F1 score, for classification problems, and mean squared error, MSE, or root mean squared error, RMSE, for regression tasks. Training and tuning, hyperparameter tuning, the process of selecting the best hyperparameters, for example, learning rate, number of layers in a neural network, for the model. Gradient descent, a method to optimize the model's parameters by minimizing the loss function using gradient updates. Deployment, once the model is trained and evaluated, it can be deployed into production to make real-time predictions or decisions. Model monitoring, ensuring that the model continues to perform well in real-world scenarios, as data distributions can change over time, a phenomenon called concept drift. Popular tools and frameworks for machine learning. Scikit-learn, a Python library that provides simple and efficient tools for data mining and machine learning tasks. TensorFlow, a powerful open-source framework for building machine learning and deep learning models. PyTorch, a flexible and dynamic deep learning framework, favored by researchers and developers. Keras, a high-level neural network API built on top of TensorFlow, making model building faster and more user-friendly. XGBoost, a popular library for gradient boosting, often used in Kaggle competitions due to its efficiency and performance. Applications of machine learning. Healthcare, medical image analysis, drug discovery, patient outcome prediction, and personalized medicine. Finance, fraud detection, algorithmic trading, and credit scoring. Marketing, customer segmentation, personalized recommendations, and ad targeting. Autonomous vehicles, self-driving cars use ML to navigate, detect obstacles, and make decisions in real time. Natural language processing, NLP machine translation, speech recognition, chatbots, and sentiment analysis. Robotics, robots learning to perform tasks by interacting with their environment.